Welcome to a lesson with Dr. Powell. Sometimes when we're integrating with triple integrals, Cartesian coordinates are really not the best frame of reference. Sometimes things can be done so much more simply. For instance, what if we had kind of a paraboloid type thing? This could be written in cylindrical coordinates simply as z is equal to r squared. If we had written this in Cartesian coordinates as z is equal to x squared plus y squared. Notice the difference. It'd be nice to be able to work maybe in this type of coordinate system here, r theta z, in contrast to x, y, z. However, our volume that we're after exists in the x, y, z coordinate system. And so what we need to figure out, just as we did for double integrals from polar to Cartesian, we need to think of from cylindrical. How do we go from cylindrical, r theta z, to here? So if we were to integrate with dr d theta dz, maybe it would be too small. Maybe we have to multiply this by something or big or whatever, but maybe it won't be the right volume calculation because it's not equal to dx dy dz. So what's the relationship between a rectangle in this coordinate system versus a rectangle in this coordinate system? And analogous to what we did when we talked about writing things in polar coordinates for double integrals, we do the exact same type of thing here. We take a determinant of the derivative, the 3x3 derivative matrix of this transformation going from these coordinates to these. Notice we have 3 outputs and we have 3 inputs. So hence the derivatives of 3x3. Take the determinant of that, and that's the relationship we need going from dr d theta dz to get to dx dy dz. And so if we're good to calculate dr d theta dz, that's perfectly fine, but we just have to multiply by that determinant so that this volume over here will be equal to that volume over there, which, I mean, in the xyz coordinates, in the shape that where we're actually doing the observation. So, because really, we picture our theta z coordinates in Cartesian coordinates in a nice way, but these coordinates by themselves are rectangular if you just kind of look at them in an integral sense. So we need this kind of conversion factor. So let's take this derivative. First, we need to know what this function looks like with 3 outputs and 3 inputs. So we have x is equal to r cosine theta, y is equal to r sine theta, and z is just equal to z. So if we were to take the derivative of this with respect to just going down through this, with respect to r, and theta, and z, for our 3 different inputs for the columns here. So we have cosine theta, sine theta, so with respect to r, 0. Now with respect to theta, we get negative r sine theta, r cosine theta, 0, and next time it's just with respect to 0, 0, 0, 1. Now you'll notice if you run through techniques of taking determinants, actually this amounts just to 1 times the determinant of this part, which we have already calculated for polar coordinates. It's just r. Actually, it's the same thing for polar coordinates. It's kind of like we're just replacing the r theta to xy, just making that replacement. It's the same as for polar. You just simply put an r in front. Very nice. Let's see how we could use that. So, for instance, let's take this right here in polar coordinates, thinking of this as z is equal to r squared, as we discussed. And then if we want to compute the volume, and let's just do it up to 4. That's a nice value there, from 0 up to there. Okay, so in our calculation, we're going to have an r dr d theta dz. And we can just kind of think about what's happening here. Theta, as you go all the way around, is going to be going from 0 to 2 pi. So maybe and z is just going from 0 to 4. So those are kind of like constants, 0 to 4, and theta is wrapping all the way around here from 0 to 2 pi. And then r, so at a particular, at a particular z value, what's happening with r? Well, r is going from 0, and it's going all the way up to, looks like this is the relationship here. It's going to square root of z. That's what's on the outside there. So as r goes from 0 to square root of z, we're going to end as we wrap around all values of theta, going all the way around. And as we go up through values of z, we're traversing the whole entire shape and representing all the coordinates. And that's exactly what we want to do in just one pass of these, in these particular coordinates in these ranges. So we have r going from 0 to the square root of z. We get this nice integral now. And we can compute this. Let's go for it. Okay, so for the inner part, we have r squared over 2, but then we're plugging in square root of z. So that'll just become, I'm plugging 0, it's going to be 0. So it's just going to be square root of z, or squared, so z, but then divided by 2 for the inner integral. Next, integrate with respect to theta. So we're going to get an extra, now z is a constant with respect to this. In fact, 2 is we could just factor the z over 2 and put it out here and just really do the integral from 0 to 2 pi of theta, which is just 2 pi. So right now we have 2 pi times this to just cancel. We just have z pi going into the last integral, 0 to 4 dz. And this becomes z squared over 2 pi, and you go from 0 to 4, which just amounts to 8 pi. So we were able to compute this volume right here by just thinking in terms of cylindrical coordinates and not just Cartesian. Thanks for watching.